Okay, so this video is going to be all about just going through the homework problems. If you have any issues with any of them, you can watch it. If you are doing just fine, that's fine too. And again, you can fast forward any problem that you need help with that didn't totally make sense. So in this first question, we've got a plane that is flying along at 96 meters per second. Okay, and it's got a package that's hanging out, and then it lets go of the package. And that package is going to continue to move at 96 meters per second horizontally, but of course gravity is going to make it fall. So, and that has to do with a property called inertia. That's going to keep the package moving forward the whole time because we don't have air resistance. So it's going to keep moving forward at that 96 meters per second. We want to know the altitude it's dropped from. So we're going to try and find our dy. What is that? Well, our equation for dy for things that are falling is just g times t squared divided by 2. Great. Again, anything that's falling from this height, whatever that dy is going to take that long to hit the ground as long as it is moving horizontally. So we need to figure out t, and that's where we're going to switch to the x-axis. So because we don't know anything about the y-axis, but we do know that our dx is 540 meters and our vx is 96 meters per second. So we can get our t there by doing dx divided by vx. Again, how long we're in the air for is also going to be determined by how far we went and how fast we're going horizontally, right? So we do 540 meters divided by 96 meters per second. And that tells us it's going to take 5.6 seconds to hit the ground. And then we go up here and do 10 meters per second squared times 5.6 seconds, quantity squared divided by 2. And we find out that we are 160 meters above the ground when we hit it. Okay. So pretty straightforward, 2 steps, 2 equations. Again, find the time from the x-axis, use that to find our information. Question 2, now we have a rock thrown horizontally from the top of a building. So here's our building. It's 22 meters high, and the rock lands 36 meters away. So whoop, goes like that. We want to know what horizontal velocity was that rock thrown with. So we're trying to find Vx. That's our unknown. So velocity in the x-axis is always just going to be our distance in the x-axis divided by how long we're in the air for, again, because we're moving at a constant speed horizontally. And we are going to get the time from the y-axis, which in this case is the square root of 2 dy over g. That's what's going to let me find how long it took me to fall. Again, anything falling from 22 meters is going to take the same amount of time to hit the ground. So square root of 2 times 22 meters over 10 meters per second squared. That's going to be 2.1 seconds to hit the ground. And we go up here, we have 36 meters divided by 2.1 seconds, and 36, and we get 17 meters per second for the horizontal speed of the ball being thrown. Okay, and again, that's all because the time it takes to hit the ground is the same for anything thrown from that height, and our Vx is going to remain constant as we're going in motion. Okay, question 3, an arrow is fired horizontally at 149 meters per second from a position of 1.62 meters above the ground. So here's our 1.62 meters. There's our speed of 149 meters per second, and whoop, it's going to do this. It's like everything else. How long does it take to hit the ground? For A, that's the time to fall, and that's always just going to be the square root of 2 dy over g. Doesn't matter how fast this arrow was fired, it's going to take the same amount of time to hit the ground. And so we would plug in this 2 times our 1.62 meters divided by 10 meters per second squared, and it's going to take 0.569 seconds to hit the ground. Second part is how far away does it land? Well, that's what we're looking for dx. And again, distance in the x-axis, because our velocity is constant, is just v times t. And if we're going 149 meters per second, and we do that for 0.569 seconds, we are going to go 84.8 meters away. Okay. Question 4, rock was thrown horizontally. Count another one of these again. We're at the top of a building. That building is 44 meters high, and it lands 34 meters away, like so. Okay. And we want to know what was the horizontal velocity with which the ball was thrown? So there we're looking for our Vx. And again, Vx is dx over t air. And the t air is going to be from the y-axis, or the square root of 2 dy over g. So time is square root of 2 times 44 meters over 10 meters per second squared. And if we do that, we find out it takes 2.97 seconds to hit the ground, or 3.0 seconds to hit the ground. So then if we go back up here, we do 34 meters divided by 3.0 seconds. We find out that we are going 11 meters per second horizontally when that ball is thrown. Second question is a little bit trickier with what vertical velocity, how fast it was going in the y direction when it hit the ground. So again, vertical velocity is going to be how fast it's moving in this direction. Again, vertical is affected by gravity. It's a free fall problem, right? So what we're really looking for is the Vy at the end. The Vy up here is going to be 0 because we're going perfectly horizontal. There's no vertical motion initially. So this is just like in free fall when a ball was dropped. We don't care about the actual speed of the ball, because the actual speed of the ball, we'll talk about in a second, is going to be a combination of Vy and Vx. But Vy is based solely off free fall. And free fall, for something that's initially dropped, that final speed is just going to be g times the time to fall, or the time in the air in this case, because all we're doing is falling. So we're going to accelerate at 10 meters per second squared. As always with gravity, we'll do that for 3 seconds. Vertically, that means I will be going 30 meters per second when I hit the ground. So what does this really mean about the speed of the ball? I'm going to talk about this just a little bit. We'll do a lot more with it later. It means at the end, we were going 30 meters per second down, but we were still going 11 meters per second horizontally in the x-axis to the right. Which way is the ball actually going? Well, it's going to be the sum of these two things. And you think about it like this. If the speed's going 30 meters per second down, 11 meters per second this way, well, it's going to bring it down, but it's also going to bring it to the right. And how much it's going to do that is given by this vector right here. This is the real velocity of the object, okay? And for those of you who might see those right triangles in there, you're going to know that v squared is equal to 11 squared plus 30 squared based on good old Pythagorean rule. Okay, so don't worry about totally getting that yet. We'll get more into that later, but understand that that's what ends up happening is you have those two components of the velocity, a horizontal and a vertical component, but the actual speed and direction of the ball is the combination of those two things. Okay. In C, would the ball take longer to reach the ground if it landed 42 meters away? No. Time is the same for the same heights. It's only based off dy. Vx does not affect time. Okay. So that's what that one, again, everything from the same height takes the same amount of time to hit the ground. That's the key. It's only based off dy. Number 5, long jumper accelerated to 14 meters per second. So here's our little long jumper. They're running along at 14 meters per second horizontally, and then they go flying into the air, okay? And they get to a maximum elevation of 0.40 meters. we want to know how far horizontally did she go. So we're looking for a dx. And we know dx is vx times t air. Here's where we're going to make a little bit of an assumption that this 14 meters per second is going to stay vx. This is our vx. Even though it's not totally true when the person jumps, some of that motion is going to go into the vertical part. We're going to assume that the long jumper, she keeps going at 14 meters per second to the right. Okay, now the question becomes t air. Well, we know that the time to fall is the square root of 2 dy over g, and we have our dy of 0.40 meters. The thing is, we're not just falling in this case. We're actually going up and coming back down. And since we're going from the ground back to the ground, the height's the same both ways, we need to double this time. Okay. If we just find square root of 2 dy over g, we are only finding the time it takes to go from this peak up here to this point, from that peak there to this point right here. That's not what we want. We need double that time to make sure we account for that way, the way up from the initial launch. So let's find T air, the square root of 2d, oh, no, I already wrote the equation. Let's not rewrite the equation, is the square root of 2 times 0.40 meters over 10 meters per second squared, and 2 times 0.8, hold on, 0.08 square root of that. So it's 0.28 seconds to come down, but again, remember we need to double it, multiply by 2, so the total time is 0.56 seconds, okay? And then we go back up here, plug that in, 14 meters per second times 0.56 seconds, and that's going to give us the 7.8 meters for dx. If you kept getting 3.9, it's because you forgot to double the time. You need to double that time because we're dealing with time to go up and time to come back down. Question 6. Tony Gwynn can throw a baseball from center field to home, a distance of 120 meters in 4 seconds. We're assuming it's thrown from ground level and caught at ground level. Okay, just for ease of everything, we want to know how high in the ball the air went. Well, that's our dy. And dy is given by gt squared over 2 for the height to fall. However, we are in the air for 4 seconds, which means we're only falling for 2 seconds. So when we do this, we do 10 meters per second squared times 2 seconds squared divided by 2, and that'll tell me the distance that I actually fell. And that's the case, we fell 20 meters. Okay, we also went up 20 meters because we're going from ground to ground. Now, the next question is, what is the horizontal speed going through the ball? That's our Vx. And Vx again is always just dx over t air. And we were told dx is 120 meters. And we were told the time in the air was 4 seconds. So nice and easy, 30 meters per second for my horizontal speed. Okay. Now the next question is, someone else threw the ball, except this one went up to 25 meters up in the air. And asks which one took longer to get to the ground, which one took longer to get to home plate. And hopefully just by looking at it, we know that the time for the second throw, the time for Finley is greater than the time for Gwynn because it went to a higher height. Prove that really quick. All we need to do is take the time to fall and double it for Steve Finley. So we're going to take the time to fall. That's going to be the square root of 2 dy over g, or the square root of 2 times 25 meters over 10 meters per second squared, which is the square root of 5, which is 2.2 seconds. That's the time to fall. So the time in the air is not that, it's 2 times that. So it's 2 times 2.2 seconds, or 4.4 seconds, which again proves that Steve Finley's throw took longer to get to home plate than Tony Gwynn's. Okay, last problem, number 7. Karen's standing on a ladder picking apples. Okay, very similar to a lot of things we've already done. The bucket's 3 meters below. It is 2 meters away, and she wants to hit the bucket. So we want our Vx, and again, our Vx is dx over T air, and T air is the square root of 2 dy over g. So square root of 2 times 3.0 meters over 10 meters per second squared. That gives us 0.77 seconds for the apple to hit the ground. And then if we know we're 2 meters away and we're in the air for 0.77 seconds, we're going to have to throw the apple at the 2.6 meters per second. So hopefully those problems make sense. If you still need help, send me an email. Let me set up a time to come talk with you. And then you'll have our practice quiz come up on a Monday.